a real pleasure to introduce today's speaker, Professor Bernard Kippelen, who last spoke in this series 5 years ago, and he tells me that his talk is going to be somewhat different, a little bit different. So obviously a lot of progress. Professor Kippelen grew up in France and obtained his first degree in solid-state physics and then a PhD in nonlinear optics at the University of Louis Pasteur in Strasbourg. He then worked at CNRS in the early 1990s before going to University of Arizona in 1994 and then coming to Georgia Tech in 2003, where he's currently professor of electrical and computer engineering and director of the Center for Organic Photonics and Electronics, otherwise known as COPE. He is a fellow of the OSA and SPIE, and it's a real pleasure to have him today.
Well, thank you very much, and good afternoon. Really appreciate the opportunity to share with you some of our latest results. It's always nice to do that at home. I just came back from a 2-week trip in Asia, and so shared with many audiences some of the results we've done here at Georgia Tech. And I think that you'll see that in the past 5 years, this field has really changed completely. And the progress that has been done is beyond our wildest dreams we could have had 5 years ago. And so hopefully I'll be able to share and highlight some of that progress with you today. As usual, always none of this would be possible without the sponsorship of various entities and organizations here. I'd like to acknowledge the Department of Energy through an Energy Frontier Research Center we're part of, EFRC, Center for Interface Science, and as well as the National Science Foundation through an STC, MDITR that has now come to an end, as well as ONR and some industrial sponsorship through Solvay. And I'm also just the reporter here, since the work I will be presenting is the work of my group members and as well as that of group members from many collaborators. Some of them are listed here, but as you will see, organic electronics, organic semiconductors is a truly multidisciplinary field, and so it requires input and participation and collaboration from a lot of different people on campus and also off campus. Lately, we've been interacting a lot with Professor Khan here from Princeton University. So what I'm going to try to do the next 50 minutes or so is to first give you a very brief introduction to organic semiconductors, review some of the fundamentals. I assume that most of you are kind of familiar with the foundation of conventional inorganic semiconductors. And so I will try to draw a parallel to see how we can use some of that understanding to somehow develop solid-state devices that are based on these organic semiconductors that are synthetic compounds, molecules, or polymers, and then give you some examples of devices that can be made from these organic semiconductors. And I will pick 3 main categories in which we've been quite active through the years, namely organic light-emitting diodes. Then I'll talk about organic solar cells, which has been a really exciting area because the progress has been tremendous and efficiencies now have exceeded 10% and they keep growing. And then I'll finish with some examples of transistors that can be printed over large area at very low cost. Okay? So the foundation of what's often referred to as organic electronics, or sometimes also printed electronics, are organic semiconductors. And one example here is one of the building blocks is that pentacene molecule. And you can see from that picture here on the right-hand side that using standard vacuum techniques at relatively low temperatures, you can actually deposit these molecules into ordered films. And through the interaction of these conjugated molecules, you can get semiconductor properties. And so it's easy to fabricate semiconducting films using various processing techniques, vacuum, if you have small molecules, but you can also print some of these materials that are soluble in solvents from inks. And so these provide a lot of opportunities in making thin films at low temperature. And as a result, of course, of the low temperature, you can grow these molecules or polymers onto any substrates. Just a little reminder about the type of molecules like pentacene that we're looking at. This is a particular class of compounds which are well known from chemists in the audience and which are so-called conjugated. Conjugation, meaning that you have alternating single and double bonds. And we will see that it's really important in understanding the semiconducting properties and the electronic coupling between these conjugated molecules when they are in proximity to one another, and you have some orbital overlap and some electronic coupling such that some of the electrons, in particular the pi electrons along the conjugation chain, can be delocalized throughout the film, and you get transport properties. And this really goes back to the electronic configuration of carbon, which you know can form single bonds, double bonds, and triple bonds. And so the interesting class of materials are the ones where you have these so-called sp2 orbitals, which lead to these double bonds, and then unhybridized pz orbitals that are perpendicular to the plane of the molecule and that are highly delocalized. And so if you look at a molecule like this, you can actually define some energy level, some orbitals, and what's important is the highest occupied molecular orbital, where at equilibrium you have two electrons with opposite spin, and then the lowest unoccupied molecular orbital, which where you can promote an electron from the HOMO to the LUMO level through, for instance, absorption of a photon, or you can also inject electrons into that orbital through some electrodes in a device. And so again, these are really important to understand the physics of these materials. Now, what's really interesting about these organic semiconductors compared to conventional inorganic semiconductors is that they actually have a lot of disorder. They are not as highly ordered than inorganic semiconductors. Now, a downside of this is you don't get the kind of performance in terms of charge mobility that you can get in silicon, for instance, or in gallium arsenide or in gallium nitride. But still, as you will see, you can get charge mobility values that are enough for these materials to perform very well in devices such as light-emitting diodes for displays, or in solar cells, or some transistors to drive electrophoretic displays or electronic papers, as it's called sometimes. Okay? And that really comes from the fact that you're actually fabricating these films at a relatively low temperature, and so there's a lot of disorder. As a result, the electronic excitations are actually quite localized, as opposed to in inorganic perfect crystals, where you have a very large, much larger delocalization. And as a result of that localization, a lot of the properties of films in the bulk are actually very close to some of the molecular properties, which makes sometimes the modeling of these properties a little bit easier, even though this is still a tremendous challenge to actually model the macroscopic properties, because these properties depend on the morphology of these films, and those are hard to predict and also quite difficult to measure. Okay? But the take-home message here is that you can actually end up with materials which are quite tolerant to defects, and this is kind of intrinsic to the temperature of the growth that's being used. So they are kind of trade-offs. Now, when you look at these materials and you start thinking about building solid-state devices, you usually have the semiconductor and then you have some electrodes. Some of these electrodes are meant to inject charges if you're dealing with a light-emitting diode, or extracting charges if you consider a solar cell, for instance, where the incident light is creating carriers. These carriers move, they create currents, and you collect them through these electrodes. And so it's really important to actually tune and pay attention to the relative position of these orbital energies with respect to a reference here, which is taken as the vacuum level. okay? And so there are two important quantities here at the macroscopic level. One is the electron affinity, which tells you where that LUMO band is located with respect to the vacuum level, and the ionization energy, which is the position of the HOMO band here with respect to that same vacuum level. Now, by analogy with conventional inorganic semiconductors, you can actually look at that HOMO band here like the valence band in an inorganic semiconductor, or you can consider the LUMO band here as the conduction band in a conventional inorganic semiconductor. And so, thanks to synthetic chemistry, chemists can design molecules that have either electron donating or electron accepting properties, and that allows to move these energy levels around. And of particular interest are molecules that have fairly low ionization energies, and those generally will be used for hole transport. Why? Because it's easy to find some metals or some electrodes that have a work function that line up with the position of these HOMO bands or the ionization energy of these donor-like compounds. And a few examples are shown here. These are small molecules. You recognize pentacene here, some phthalocyanines. These are polymers, so these are very long chains of repeat units, and the advantage is that these polymers are soluble in organic solvents, and so you can make inks, and you can process these inks into thin films using standard printing or coating techniques. Okay? On the other hand, you can also, through chemical design, make molecules that are electron deficient or acceptors, and those generally have fairly large electron affinities, and so you can push the LUMO level sufficiently down here away from the vacuum level so that you can start to line up with some low work function metals such as calcium, for instance. And so again, this will be very useful in order to make solid state devices where you need to either inject very efficiently holes and electrons or extract efficiently holes and electrons. And so, of course, the mobility, which is an indication on how fast these carriers can move in a solid state, is a macroscopic property, and its magnitude or its value is going to depend on the level of coupling of these conjugated polymer chains or small molecules. And so the mobility values can vary by many orders of magnitude and will strongly depend on the morphology of these materials in a solid state film. And so you can see typically in some amorphous materials, the mobility values are typically in the range of 10 to the minus 3 centimeters squared per volt second. If you take more crystalline materials, we can get now materials that have mobility values of the order of 10 to 20 centimeters squared per volt second. Okay, so we're still orders of magnitude lower than what you get with inorganic semiconductors, but we're not competing here with silicon. We're looking at alternatives where you can really print these transistors over very large areas and at very low cost on any substrate. So that has been one of the drivers for printed electronics, is that the flexibility and the ability to print these materials at low temperature using either roll-to-roll manufacturing or batch-to-batch, doesn't matter. And what's really also driving that whole industry is the ease of integration of different functionalities. Okay? Because this is all done at relatively low temperature on metal foil or on plastic substrates. So it's easy to integrate some energy supplies in the form of flexible batteries or flexible solar cells. You can add a display, you can add some light sources, you can add some sensors and so on and so forth. And of course, you don't have to be dogmatic and use only organic materials. You can, of course, also do a lot of what's often referred to as soft electronics, where you can combine high-speed circuits, for instance, for communication, and combine this with some of these other functionalities on the same chip. Okay, so all of this is possible. And well, this is why a lot of people are so interested and excited about that emerging technologies, because if you look at the market forecast for printed electronics, it's a very sizable market in tens of billions of dollars. These numbers here, of course, vary a little bit depending on the market research company and the report that's coming out. But you know, the exact number is not that relevant, but it's really the average size. And also, I think what's important to realize here is that this is still, we're just seeing the tip, the emerging tip of that iceberg, and it's supposed to grow in the years to come, even though, as you will see, OLED technologies have come a long way and have now grown into a massive market. Okay, so with that background and that introduction, let me now highlight a few examples of some of these solid-state devices that we've actually made in my group together with our colleagues. And the first area is organic light-emitting diodes. Now, this is the most mature segment of this industry, and probably some of you own an OLED display because the latest phones, in particular the Samsung Galaxy, have these active matrix OLED displays. And you know, that technology, these new cell phones have many advantages over conventional LCD displays, and so they are really taking the mobile display market by storm. And you know, that so-called long-awaited OLED era that we've been talking about for the past 20 years has now arrived, okay? And so you can see here some of the market research projections about the size. The units here are thousands of dollars, so you can see we're really talking about billions of dollars for that emerging industry. These are real products. These are kind of concept products, but Samsung is actually working on the commercialization of a flexible phone. I've seen some prototypes. It's really impressive. And so there is, of course, always the quest for new materials and better devices with increased efficiency. It never stops, because the more light output you can get, the longer your display will operate, given the energy that's stored in the battery. And so if you look at these OLED technologies, they're basically comprised of usually a stack of 2 to 3 layers, where you have a high work function electrode, typically here the anode, which injects holes into a hole transport layer. On the other side of the device, you have a low work function metal, such as calcium or some lithium fluoride based materials that inject electrons. And then these holes and electrons, they form excited states in that emissive layer. And the photons that are emitted usually through the bottom here of the substrate on which the OLED is fabricated, which is ITO-coated glass. Okay? Now, when you consider the maximum efficiency that you can get out of an organic electroluminescent device like this, in the early days, people were looking at fluorescent materials. And so the only materials that actually emit light are singlet states, okay, for fluorescent materials. And due to symmetry reasons and transition rules, you can't have emission from the triplet. Now, statistically, if you look at how many singlets you create, because the charges that you inject have a spin, you're actually only creating about 25% of singlets and 75% of triplets. So in the early days, you were basically wasting a lot of the states that were formed because they were triplet in nature. But then Mark Thompson and Steve Forrest came up with a solution to that problem in the late 90s, and they introduced some organometallic electrophosphorescent dopants, where due to the presence of a very heavy element in these molecules, you have a strong intersystem crossing, and if you dope these materials into a matrix, you can actually harvest all the singlet states, which then turn into that mixed singlet triplet state from which now you can have emission, and as well as harvesting of the triplet through some Dexter energy transfer. And so as a result, you can actually harvest 100% of the excited states, and as you will see, make materials that are very efficient, or devices that are very efficient. Now, what limits the overall efficiency of the light that's emitted here also are some wave guiding effects in the substrate here due to total internal reflection. But they are, as we will see, there are solutions through new device architectures. So next, I'd like to give you a couple of examples, a few highlights of some recent progress. And the first one I picked here is the work that we have done in collaboration with Seth Marder and his group, where instead of designing molecules that have either Hall transport or electron transport properties, they actually design molecules which have both, okay? And these are so-called ambipolar molecules and corresponding polymers. You can use that as a building block and put it into a polymeric structure. And you'll see that such molecules are actually comprised of some moieties here, such as that carbazole group, which is a well-known electron donating group, which is widely used in Hall transport materials. And that other group here, which is oxodiazole, which is electron deficient, and that usually has good electron transport properties. And you can see from these quantum chemical calculations that were done in the group of Jean-Luc Breda that the HOMO orbital here is actually located on one of these carbazoles, while the LUMO orbital is actually located on that oxodiazole. And so to illustrate the nice properties of these molecules, here's a device example where we start with an ITO-coated glass that's treated with plasma in order to increase the work function. And then we have a Hall transport material here, which contains several carbazole moieties, and one of these ambipolar hosts that is doped with that iridium phosphorescent molecule. So you can see these are these molecules that harvest all the singlets and all the triplets, and which electrophosphoresce with nearly 100% photoluminescence efficiency. And so if you look at the current voltage characteristic and the luminance of these devices, you can see that they're extremely high. At 100 candelas per square meter, you have nearly 30% external quantum efficiency, which in a device like this, in view of the wave guiding losses in the substrate, translates into internal efficiencies that are close to 100%. Okay? Now there's a little bit of a roll-off here, and as you go to higher voltage and higher current, the efficiency starts to drop a little bit, but you can see that at 10,000 candelas per square meter, you still have efficiencies, external efficiencies in excess of 20%. And so these are some of the most efficient organic light emitting devices that have been reported so far. Those actually emit in the green, but we've also made blue emitting materials. Here's another example with a different phosphor that emits in the blue-green. And here again, you can see that, if you apply, let's say, 5 volts to a device like this, you can get a luminance that is several thousand candelas per square meter, and with efficiencies that are, again, larger than 20%. So very efficient materials for OLEDs. Now, a lot of these early devices actually, as I said earlier, are built in a geometry where you start with a transparent substrate, which is ITO-coated glass, and ITO is used as the anode. And then you have emission through the bottom of the substrate. Now that has multiple problems or barriers. One is that because you're emitting through the substrate, and because in an active matrix display you always have some electronics to drive the pixel, you're actually limited in the pixel aperture ratio. So it would be desirable to actually have something that emits from the top, such that you're no longer bothered by the limited pixel aperture ratio, and as well as some of the wave guiding losses that you might have in the substrate. Another desirable feature also is, rather than having a diode like this where you have the anode at the bottom, you'd like to actually, because these OLEDs right now are driven by transistors that are N-type or NMOS. These are N-channel transistors, low temperature polysilicon. or some metal oxide semiconductors. And so because of the geometry, you'd like to build the diode on this side here. You don't want it to put it on between the source and gate because that's usually where you control the current that flows through the circuit and so through the pixel. And so what you'd like is to basically have it biased in a way such that the cathode here is at the bottom, compatible with some of the aluminum electrodes that are being used for the circuitry. And so that requires to flip the direction of the diode and as well as having it top emitting. And so this has been quite challenging for a lot of time, and many people tried over the years, including ourselves, to flip the structure over. And it was a real challenge, but lately, two of my students here, Ehsan and Keith, were very lucky and actually were able to demonstrate so-called inverted structures where the light is emitted through the bottom and that are also inverted in the sense that the cathode is now at the bottom and that aluminum electrode here could be actually directly connected with the backplane circuitry in an active matrix display. You'll notice here that there is no ITO anymore, which is also good because ITO is brittle, and so if you want to make highly flexible displays, you're limited if you use ITO, and ITO is also quite expensive. And the light is emitted through that very thin top metal layer. It's a 20 nanometer thick gold layer that has a transmittance of the order of 50%, but you can still get a lot of light out of these devices. More details you can find in these two papers that were just published recently, one on these green emitting devices, and we just had a paper up here last week about blue emitting devices, which I won't have time to talk about. But here are the efficiencies and the efficacies, and so you can see despite the limited transmittance of that semi-transparent top gold electrode, we can get extremely high luminance levels and the corresponding external quantum efficiencies and the current efficacies are now at low luminance, actually exceed 100 candelas per amp, which is close to a record. Now, how do we go beyond this now that we've achieved nearly 100% internal quantum efficiency? Well, one strategy that had been employed in the past is to actually stack some of these LEDs the same way you stack solar cells and you make multi-junction solar cells. And what that buys you is that you can double the amount of light that is being emitted at a given current, because the current that flows through these two LEDs that are connected in series goes through two different line emitting junctions here, and so you double the light output. So you can get 200% efficiency in some of these devices. Of course, the trade-off is that the voltages that you will be applying here to get to the same level of current is higher. So the power efficacy is going to be similar, but the current efficacy, the number of candelas that are emitted per unit current, is going to be double. The other advantage of stacked geometry like this is that now for the same luminance, because you get emission from two layers, you can also run these devices at lower current, and that generally leads to longer lifetime, because the lifetime of these devices usually correlates by the number of electrons that are flowing through these structures. Okay, and so these are actually unprecedented. This is the first demonstration of such stacked inverted bottom cathode devices, and you can see if you compare a single junction device with a stacked 2 OLED device, you could nearly double the efficiency. Here is a plot of the current efficacy. Again, a pretty nice efficacy in a single layer inverted structure. If you have these two stacked OLEDs, you can nearly double, or you can actually double, in most cases, the current efficacy, and now again get very high values. Okay? So let me switch gears and start talking about the other topic, which is really hot right now, which is organic photovoltaics. I don't think I need to elaborate on the motivation to develop low-cost, clean energy sources. And so organic photovoltaics, some of these concepts were actually introduced in the early 80s also by Qing Tang. And just to give you kind of a calibration at the time, the power conversion efficiency of these devices was of the order of 1%, to be compared to nearly 20% now with some of the crystalline silicon solar cells that are being fabricated. And so, one of the key metrics here in order to compete and make that technology attractive is to increase the power conversion efficiency. And for this, you really need to optimize simultaneously the photocurrent that is produced. Now, this is a device that operates in the photovoltaic mode, so you have simultaneously a photocurrent as well as a photovoltage, so it's the product of that photovoltage and the photocurrent that gives you electrical power. And you can actually define the efficiencies here as the product along that curve where these two values, photovoltage and photocurrent, are maximized. Or it's also convenient to define it as a function of the product of these two quantities here, which are the intersects with the horizontal and the vertical axis, namely the open circuit voltage and the so-called short circuit current. And then you have to introduce that so-called fill factor, which is basically the ratio of Vmax times Jmax, which is that gray shaded area divided by the area that's defined by the product of VOC and the JSC. And so just to put organics into perspective compared with some of the other PV technologies, there are good news and bad news. Okay? The bad news is that if you look at the efficiency compared to some of these other photovoltaic technologies which have been around for a long time, we're still at the bottom. Okay? But the good news is if you actually look at the slope here at which progress is being made, it's one of the largest. Okay? And nowadays, actually this year, efficiencies have now exceeded 10%. There have been several reports, independent reports, one on polymers, another one on small molecules from a company, Heliatech here, that's based in Germany. And so these efficiencies keep growing, and so really exciting time for organic photovoltaics. Now, how do these work? They actually have some particularities, but in a few words, without going into the details, you can draw a parallel between a conventional PN junction crystalline silicon solar cell, where the junction here acts as a membrane, and the function of that membrane is to spatially separate holes and electrons that are being generated in different parts of the solar cell. And then if you're successful in separating the electrons here, you can define a quasi-Fermi energy for the electrons. Same for the holes. And then the difference in the quasi-Fermi energies here at the charge collecting electrodes, that gives you that photovoltage, which is important to have a solar cell generating power. In organic materials, this goes back to these HOMO and LUMO levels, which I drew earlier in some of these diagrams. And the membrane here is obtained by forming heterojunctions between dissimilar material, one that usually has donor-like properties, another one which has acceptor-like properties. And again, you're generating excitons, which are bound electron-hole pairs. They have larger binding energy than excitons in inorganic materials, so you have to break those up. But when they break up, you can inject electrons into the electron transport layer and holes into the hole transport layer. By analogy, again, you're forming quasi-Fermi energies for electrons and holes, and you get your photovoltage and the current through the diffusion of the carriers in the device. For more details, you can check this review article that we wrote with Jean-Luc Breda a few years ago. And so here's the first example of a typical organic solar cell. So like for OLEDs, we start with an ITO-coated glass slide, which here is coated with a conducting polymer, which has a work function of the order of 5 eV. And so that acts as the hole collecting electrode. And then that heterojunction, in this particular case, is a mixture of that hole transport material, material with fairly small electron ionization energy, And the acceptor here, or the electron transport material, is that soluble fullerene, which has a fairly large electron affinity. And you can see the top electron collecting electrode is a low work functional electrode, and typically it involves the use of metals such as calcium, which have the advantage of having a low work function, but unfortunately these materials are highly reactive, so you have to protect these cells extremely well. But you can see you can get efficiencies here in the range of about 6% in a cell like this. Okay? Now, as before, in recent years there has been a trend to actually turn these devices upside down, and that's been driven mainly because that top electrode with highly reactive metals such as calcium makes the packaging of these devices very challenging, and so that increases cost. And so if you turn the device upside down, you can have that lower work function electrode that's buried in the device, so it's better protected. It somehow improves the stability of these devices, but still, having calcium there is a major challenge. And so one of the strategies we've developed recently in trying to replace highly reactive, low work function metals such as calcium is to do some surface modification. And the first example of some surface modification here is shown. This is work that J1 initiated, and he was using that polyvinyl pyrrolidone material initially as a surfactant to disperse some TiO2 nanoparticles. And you can see this is a non-conjugated structure, so it doesn't really have interesting electronic properties. But what he found is that when he was actually using just the surfactant by itself, even without the TiO2 nanoparticles, that he could make nice inverted solar cells. And when he did some Kelvin probe measurements of ITO that was modified with a very thin layer of that PVP material, he could see that there was a significant reduction in the work function sufficient to turn ITO into a low work function electrode and an efficient electron collecting electrode. So you can turn the device upside down. Then we were kind of wondering what was going on, so we sent these materials to Antoine Kahn at Princeton, who did some UV photoemission spectroscopy. And you can see here from the shift in the onset of the secondary electrons in the UPS experiments, that corresponds to a shift in the vacuum level, a downward shift of the vacuum level, which is due to the formation of a surface dipole through the physisorption of these polymers onto the surface of the ITO. And so when we looked at the structure of that PVP, I said, what could possibly go on? Started talking with our colleagues in chemistry, and the suspect was that nitrogen atom there. And so we picked up the Aldrich catalog and started looking for materials which contained a lot of amines. And one of them is that PIE material, which is widely used for gene delivery, gene therapy in biology. It's also not, it's a safe material to work with. And then when we started dipping ITO or some other electrodes into dilute solution of a branched polymer like this, you can see the shifts that were observed of the vacuum level in UPS experiments were huge, up to 1.5 volts, okay? And so you can see this is the result on ITO, so you have a huge shift. It also works on a conducting polymer. pH 1000 is actually a P.PSS grade, high conductivity grade. You can again turn a conducting polymer into a low work function electrode, or you can use inert metals. You can use gold and just dip it into a dilute solution like this, and you'll end up with a stable, low work function electrode. And so these materials are actually fairly stable, up to 200 degrees C, which is usually gives you enough flexibility to work with plastic substrates. Typically, a lot of these process temperatures never exceed 150 degrees C. So these PIE materials are sufficiently stable. But really what's remarkable and game-changing about these materials is now you have electrodes with a work function that's in the range of what you can usually get with calcium, but it's air stable. Okay? Now that changes everything, because now you can manufacture these devices in air rather than in glove boxes or in vacuum. The packaging is going to be much simpler, so you save a lot in cost. It's really disruptive in terms of the improvements it has on solar cells. And so here's an example on how that surface modification with PIE can be implemented in an inverted structure where ITO is modified, which becomes the electron collecting electrode. The active layer is a mixture of these compounds, and for the top electrode we have that molyoxide silver, and you can see you can get very nice solar cells with efficiencies of the order of 6.5%. However, when we realized that you can actually use this to also modify conducting polymers and make low work function conducting polymers, we thought, okay, so we can make completely plastic solar cells. And so this is work that we published in Science last April, and there have been a lot of stories about these completely plastic solar cells. If you want to read them, there's actually an article on Forbes.com about them. And what's nice about these old polymeric solar cells is they really have truly unique mechanical properties. You can bend them down to a bending radius of just a few millimeters, and it's very stable. And again, this is in materials that require much less packaging, and you still have to protect the active layers somehow, but it's a completely different story because you don't have lithium fluoride or calcium in your device structure anymore. And so here's just kind of a summary that shows that the method is fairly universal because it's physisorption as opposed to chemisorption, so it doesn't really depend on the chemistry of the surface. And so you can see the green bars here are the initial work function values of various electrodes, and after PIE modification, you can see the significant change. It drops with zinc oxide, for instance. You can go down to 3.1 eV, which is very close to what you have with calcium. Okay, as for OLEDs, one strategy to actually increase the power conversion efficiency of solar cells is to fabricate tandem cells, where you stack different cells on top of one another, because you can use materials that absorb in different parts of the solar spectrum. The challenge, of course, is that if you have these cells collected in series, you're going to have an overall open circuit voltage that will add up, but you also need to actually get the same current that is flowing through these two devices, or the overall current is going to be the minimum value of the current that's produced in either of these two cells. But here you can see very nice tandem cells, where in the middle, what's critical, what I forgot to say, is very often the biggest barrier are these so-called charge recombination layers here in the middle that connects these two layers. And here you can see that we actually shown that you can use a conducting polymer layer modified with that PIE on one side, and those make very nice recombination layers in these tandem cells. And so here you can see this is our champion cell. It has a power conversion efficiency of 8.2%. What's also very nice is that we have fill factors here that are larger than 70% and actually larger than the individual fill factors that you can get in these cells if you make single junction cells with some of these materials. And so we fabricated many of such devices, and if you look at the average values here over 25 devices, we still get the fill factors close to 70% and efficiencies in the range of 7 to 8%. Okay, the last part, the last few minutes, is just to give you a few highlights about another interesting area, which is the use of these organic semiconductors to build transistors. And I would just focus on one small part here, which was the discovery of a very efficient bilayer gate dielectric system, which yields transistors with unprecedented stability. One of the big challenges with organic semiconductors, and this is a question that always comes up, is say, okay, this is nice, but what about stability? Okay, because of course some materials such as pentacene, for instance, are quite sensitive to the environment, oxygen and moisture. They can undergo photooxidation. But if you design your molecules properly, so these are, for instance, molecules that were designed by John Anthony at the University of Kentucky, and he introduced these side groups here to protect these sites here on the pentacene molecule, which are the ones that usually undergo photooxidation. And molecules like this have a much higher photostability. And so here you see the cross-section of this transistor. You have a substrate, you have bottom source and drain electrodes, you have a semiconductor layer that's spin-coated on top of these electrodes, and then you have your gate dielectric and the top gate electrode. And so the conduction channel is at that interface between the semiconductor and the gate dielectric, and so you can modulate the current that flows between the source and drain electrode here by applying a gate voltage to that top electrode. You see here a typical transfer characteristic of a transistor like this, average mobility values of the order of 1 square centimeter per volt second. But really nice about these transistors, and that was totally unanticipated, is that they are extremely stable. And so you can see here, these are 20,000 on-off cycles measured for these transistors, and there is no degradation, no shift in the threshold voltage, which is really important. And so to illustrate the stability of these transistors, I have a little movie here that shows that, just leaving these transistors on the shelf for about 11 months, you would put them back in the system, they're still working. But the postdoc who was doing his measurements was tired of seeing no changes. So he put them in a plasma chamber for 5 minutes, and to his surprise, he wanted to really destroy these transistors. They were still working, okay? Next, he actually he immersed them in water for an hour, and then took it out, just dried it a little bit with nitrogen, put it back into the semiconductor analyzer, and the transistor is still working, okay? Now, if you look at closely the details here of what these pretty severe tests do to the transistor, this is again the transfer characteristic as measured in a fresh device and measured in nitrogen in a glove box before the device is exposed to the environment. If you expose it to air, you have a small shift in the threshold voltage here, but it stabilizes after some time. But what's really truly amazing is when you look at the transfer characteristic before and after the 5-minute plasma treatment. Okay, that was really a big surprise. That was a shock to us that there's actually no change. Likewise, if you look at the transfer characteristic before and after immersion in water for hours, and now we do that hours or days, there's absolutely no change. So extremely robust. To be honest, we don't quite understand exactly yet what's causing that incredible stability, but it shows that you can make printed organic semiconductors with good environmental and operational stability. And because of that stability, we also started to develop sensors with these transistors, and this is, to the best of my knowledge, kind of the first sensor that is non-destructive. And you can see, because when you run these devices in air, or if you run them under continuous water flow, there is no change into their electrical characteristics. And so if you add some analytes to the liquid here, you see now you can have different changes, or you can have changes in the electrical characteristics. And, but the important point here is fully reversible. There is no degradation of the transistor as opposed to a lot of the sensor work that's been done in the past, where we basically used the transistor as a sensor because it was degrading in contact with oxygen and moisture. And so just to show you that we can process these materials as inks and actually fabricate transistors using conventional printing techniques such as an inkjet printer. I just put a slide here that shows an example of a transistor that's fabricated with that inkjet printer with a polymer. Very nice transistors, threshold voltages, near zero, mobility values of the order of 0.1 centimeter square per volt second. This is with a polymer. And here, this is kind of our latest material that was synthesized in Seth Marder's group, and which is a large molecule which is soluble, so you can make inks. But this is a monodispersed material. You can reproducibly make always exactly the same structure, while, as you know, with polymers, you always have some batch-to-batch variations because you don't always have exactly the same molecular weight. Okay? So that brings me kind of close to the end of my talk. And before I summarize, I thought I also take a minute or two to somehow discuss what I believe is where this is going. I think we have now reached a level of performance where it's fair to say that we're doing as well as amorphous silicon, or we even exceed amorphous silicon in terms of the stability of these materials. But as we think in terms of the concept of having intelligence everywhere and printing massively some of these materials, I think we also have to worry about some of the other aspects of the life cycle of these products. And so think about how we can recycle some of these materials. And there are actually a lot of opportunities to replace some of these substrates, such as, for instance, the plastic substrates that I use with some materials that derive from natural products, just such as cellulose nanocrystals or nanofibrillated cellulose. And you can make transparent substrates that work actually quite well and that are derived from sustainable sources. And so I think there's a great opportunity here ahead of us to also try to replace some of these functional materials that derive from petroleum chemistry with naturally derived materials. And so with this, hopefully I've convinced you that organic chemistry really allows for the synthesis of molecules and properties with some unique semiconducting properties that can be used to make highly performing solid-state semiconductor devices such as LEDs or solar cells or transistors. There's no doubt in my mind that with the current progress and some of the investments that are being made, in particular in Asia, in active matrix OLED technologies, that in the near future, LCDs will still be around for quite some time, but in the long term, I think that OLED technologies will become the technology of choice for displays. And there's also a lot of potential for using solid-state light sources. Right now, the cost, of course, is still a major issue for that application. And I also think that in view of the progress that's being made in organic photovoltaics, that there's a potential future for that technology. 10% is okay, it's not enough. 10% right now is obtained in very small area laboratory cells. We have to demonstrate this in large area modules, so still a lot of work to do, and maybe some market entry in about 2020, maybe a little bit earlier. But I think they will become part of the energy mix, and I also believe that there are tremendous opportunities for future research on materials that are recyclable and that derive from natural products. So with this, I'd like to close and thank you for your attention, and I'll be happy to try to answer any questions. Question? Oliver?
Thanks for the talk. A question regarding the sample sizes. When you characterize efficiencies of the solar cell modules, but also of the LEDs, is that typically done for standard sample sizes and the area, or is this not dependent on sample size?
Yeah, so it does depend on sample size. Now, the dependence is different for OLEDs and for solar cells. Okay? For OLEDs, you have to worry about the uniformity of the potential, because you want to stay on the same point of your current voltage characteristics. So as long as you don't have a significant voltage drop that is caused by how you make contact, it's not that important. In a solar cell, however, as you increase the size of the device because you're integrating the flux, you actually increase your current density. And so your overall losses get higher. And so the efficiency of the solar cell is going to be very sensitive to the series resistance that you introduce when you make the solar cell larger. And that's why, we use very small cells, but when you move towards modules, which we have, I didn't have time to discuss that, you usually segment the module into stripes, and you keep the width of the stripes sufficiently small such that the overall current that is produced stays under a given threshold where you don't have much joule losses as opposed to the overall power that gets generated. So one of the challenges right now is when you go from single cells to modules is the way these stripes are connected. There's a lot of dead space. And you introduce also additional resistance because of the connection. And so right now, the most efficient cells have exceeded 10%, but if you look at the efficiencies of modules, they are more around 4 or 5%. So we need to close the gap, but we have some ideas how to do that.
But that means then also in your lab, when you do the testing, you have one set of masks, basically, and you use that for the different developments so that you can directly compare.
Yes, yes. If you work, it depends a lot on the sheet resistance of the electrode that you use. So if you have ITO-based devices, we work on samples that are usually a square inch, and the sheet resistance is about 15 ohms square. So it's not a problem if you have a 15 ohm per square sheet resistance. In the old polymeric cells, the efficiency is right now a little bit lower because the fill factor is not as high because we're using conducting polymers, and conducting polymers have a sheet resistance of the order of 100 ohm per square. And so here, even in our small area efficiency, we see the effects of series resistance. But if you move to a stripe-like module, then you alleviate some of these problems.
Can you get optical gain and lasing in organic materials?
Yeah, that's a very good question. So, I've been working on OLED since the 93. And at the time, this was shortly after, both Ching Tang at Kodak had reported electroluminescence in small molecules, and then Richard Friend at in the University of Cambridge had published their results on polymers. And the first grant we got was to try to demonstrate lasers, because we thought, well, we have LEDs, what about lasers? And there's been a lot of work in making lasers, and optically pumped, is quite easy. You can get fairly good gain, but one of the challenges is in getting electrically pumped lasers. And the main problem is that when you inject high current densities, these carriers that you create are basically radical ions, radical cations and radical anions. And these actually absorb, so they introduce additional losses. So it's very difficult to keep low losses and have very high current injection. So that makes the lasing very difficult. And there was one report by Henrik Schoen in the early 2000s at Bell Labs, but I don't want to go into the sad details of that story because it was fraudulent, but nobody's been able to report electric pumped laser yet. I think it's going to be very difficult.
So you showed in the talk at the beginning an example of a flexible cell phone, which is not commercialized yet, but could be very neat. But it seems to me that all the other applications you showed, you don't really need the device to be flexible. So I'm just wondering,
yeah.
Is the flexibility something important?
Well, for some products it is, right? For others it's just a matter of mass production. I mean, even if you have a rigid flat form factor, but if you could do mass production using roll-to-roll, that will lower the cost, okay? But on the other hand, if you want something that's conformal, or when you think about very large TV screens, right now, if you buy one of the largest TVs at Costco, you can't fit it in your car, okay? But if you can buy it in a tube, and you can just roll it up and down, and you roll it up when you don't use it anymore, and it saves a lot of wall space in your living room, that's one possible advantage. But this is still far out there. But I think we're getting there. The display, I was at Samsung 2 weeks ago, and one of their target now is to go towards very large screens and also ultra high resolution. We're talking about 1,000 pixels per inch. Okay, and so a lot of the shadow masking that's being used right now doesn't scale out to that kind of resolution. But with very fine, printing or maybe nano imprint lithography and things like that, there are ways to go to very high resolution.
So flexibility is very important for manufacturing more than the actual.
Yeah, I think that's, and I'm not a marketing expert. I think that's a question left for market research companies. But, in the early days, a lot of people were talking about making flexible electronic paper. Well, it turns out that people are perfectly fine with an iPad. It doesn't have to be flexible. But things change. It's hard to predict. That's kind of more linked to social behavior and more than just the technology. But the potential is here. If there is a need for something that's highly flexible, it could be made into a flexible form factor. The question whether or not that's appealing to customers, that's a different question.
Let's thank Professor Kippelen one more time. And then I'm sure